What's up, Algebra 2 students? Let's do the Unit 11 review. This is when we discovered that to undo an exponent, you use a log. To undo a log, you use an exponent. They're inverses of each other, similar to a square root undoing a square, or a square undoing a square root. If you have an exponent and you'd like to get rid of it, maybe solve for x, we can log both sides. Paying attention to this base, we will log base both sides. Log base of 4 to the x just leaves us with x. Here we have log base 4 of 4,096. We can type that into our calculator, either using our friend, Mr. Log Base, or typing in log of the top number, close your parentheses, divided by log of the bottom number. If you're going to do division, that works. If you're going to use the fraction button, that works. Just like close off your parentheses just to be safe, and you get your answer 6. We won't always get whole number answers when using logs, but we will sometimes. Okay, I got 6 to the power. I don't divide by 6. It's 6 to the exponent of x. To get rid of the exponent, we will use a log. It is the inverse function. It will undo. Logs undo exponents. X equals log base 6 of 1296. Let's use log 1296 divided by log 6. And that's 4. Okay, to get rid of a 10 to a power, let's log base 10 both sides. Log base 10 of 10 to the x is just x. Log base 10 of 1 over 100 is going to be negative 2. Now, log base 10 is just the same as log. If you use the log button, you are using a log base 10. So I can just type this in. You can type it in any other way. You don't have to do the base 10, but I'm going to put it there anyways. You can either leave this blank and write negative 2, that's fine, or you do base 10. Sorry. Log base 10 of 1 over 100 equals negative 2. 2 to the x, don't divide by 2, log base 2. And we get negative 5. Log base 2 of 1 over 32 is negative 5. Great. Now, to get rid of a log, we use an exponent. This is when we use the exponent button. But base 3, use a 3 to the 4th. 3 to the 4th. Not 4 cubed. 3 to the log base 3 goes away, leaves us with x. 3 to the 4th. 81. Log base 5. Get rid of the log base 5 with a 5 to the. We'll use exponents to undo logs. Exponents undo logs. Logs undo exponents. 5 squared. 5 squared. Not 2 to the 5th. 5 exponent button squared. 3 exponent button 4th. Okay? If you see ln, you know that it's a log base e. It's just used so often that it gets its own button. So you want to get rid of an ln, you use e to the power. E to the power undoes the log base e. E to the first is my answer. E to the first. E over the division symbol to the first is this number 2.71828, which shows up naturally in a lot of mathematics when we use infinity. If you don't see a base and it's log, since it's used so often, it gets its own button. It's log base 10. So undoing a log base 10, you do 10 to the. 10 to the. 10 to the log base 10 goes away. You get x equals 10 to the negative first. 0.1 or 1/10. Okay. Since logs and exponents undo each other, they work similarly to each other. Here are some rules. If you have exponents like x squared times x cubed, you can write that as x to the fifth. What that turns into is this log property that when you see addition between two logarithms, like you see addition between two exponents, it means multiplication. Which means you can write this as 1 log, keep the base, but 4 times 5, 20. Okay? Another exponent property. Isn't this the same as x cubed? You cancel 2 x's, you cancel 2 x's, this is x to the 5 minus 2. That turns into the log property that when you see subtraction, you can think division. You can compress the 2 logs and turn it into 1 log. 18 divided by 3 is 6. Okay? Last property. If you know how to do x squared cubed, and you're like, oh, that's the same as x to the 6, 3 times 2. It's like you could take this multiplication and move it up to the power. If you see multiplication, you can move that exponent up. So it's log base 2 of 3 to the 4th. We did this earlier. 3 to the 4th is what, 81? So this turns into log base 2 of 81. Now I don't care what that's equal to. I want to simplify using the log properties. Now you got a bunch of different things going on at the same time. Well, let's just go one at a time. Let's work with this 2. Now it's 4 squared. And I get 16. So this is log 16 plus log 9 minus log 3. Okay, well, addition means multiply. Let's multiply 16 and 9. Log 144. Let's look at the subtraction now. Oh, subtraction means divide. Let's divide 144 by 3. 48. My answer is log, you can put the 10 or not put anything there. Base 10 of 48 is the same as that. Now, heads up, you can check all your answers. Is log 48 the same as 2 log 4 plus log 9 minus log 3? Yep, I got it right. This can be done with all of them. Now, at the same time, sometimes we're going to want to expand logarithms. For whatever reason, we're just going to go in the opposite order, okay? We see division inside one logarithm. We'll do the expansion property. Division means subtraction. So instead of like subtraction, think division. If you see division in a logarithm, think subtraction. This is expanding. Log base 2 of 3 to the 4th minus log base 2 of 4 to the 5th. Cool. What else can I do? Well, instead of what I did here, which is to bring it up, I could switch this and bring this down. So another thing going the opposite direction with my properties would be bring those exponents down. You get 4 log base 2 of 3 minus 5 log base 2 of 4. Here, you might not see it, but this is inside of one logarithm. I should have put parentheses around there. You see multiplication inside. Okay, inside a logarithm, if you see multiplication, you can split it up and go the other way and add. So like 2 logarithms with a plus, plus means multiply. If you have multiplication inside a logarithm, it means plus. You just go in the opposite way. So I have log x to the 4th plus log y squared. and then do our property where we bring down the exponent, giving me 4 natural log x plus 2 natural log y. All right. These questions are really the same as the initial questions, but I'm not allowed to get rid of the exponent until the exponent's isolated. So it's like we're solving equations. We were solving equations before, but make sure we isolate or get x and what it's attached to by itself. We're solving equations. What's happening to this x? Well, 4 is being taken to the power of x, and I'm adding 5. It's all on the same side. What should I do? Subtract 5 from both sides of the equation. 69 minus 5. 64. Now, I want to get x by itself. It's in the exponent that has a base of 4. Get rid of the 4 with a log base 4. Log base 4 of 4 goes away. We just have x equals log base 4 of 64. Log base 4 of 64 is, I believe, 3. Log 64 divided by log 4. Close your parentheses. Oh, it's 3. Oh, that's what I said. Not all of our answers are going to be nice numbers. Here's going to be our first decimal. 3 e to the x. Now, what's important is that this is read 3 times e to the x. Okay. We always like to get rid of stuff being added first before we get rid of the stuff that's being multiplied. Now, don't log 3e. 3 times e to the x. Divide by 3 first. E to the x equals 60 divided by 3 is 20. Now, log base e to get rid of the e. X equals log base e of 20. Oh, log base e is the same as the natural log. Natural log 20. The natural log of 20 is the same as 2.9957. Probably on your test, I'm going to give you like half credit for this and then half credit for typing it in right. You got to make sure you type it in right. Okay. What's bothering the x? Well, it's in the exponent of 5. It's being divided by 6 and subtracted by 4. Let's get rid of the stuff being subtracted first. Let's get rid of the stuff that is being divided by multiplying by. Okay? Get rid of that first. $72. Now, let's not worry about the 2x. Let's get rid of this 5 by log base 5ing both sides. Now that will get rid of this, but I still have 2x left over. I'm going to move over here. 2x equals log base 5 of 72. So that's, I'll use log base this time. Log base 5 of 72. 2.657. I will then divide by 2, take that number and divide it by 2. And I get 1.328. Okay? So, it wasn't just x in there. We had to do one extra step. Here, we got to subtract. Make sure you understand that it's not 50e to the 0.5x, it's 50 times e to the 0.5x equals 1200. Get rid of the 50 first by dividing. $24. Log base e, or natural log both sides, natural log 24. Over here on this left side, 0.5x stays. This is 3.178 dot dot dot. Take that number, divide by 0.5 to solve for x. 6.356. If you have a log, you want to get rid of the log? Well, isolate the log. Use an exponent to get rid of the log. Add 3. You could move this 2 up if you wanted to. You could use a log property if you wanted to, but this is 2 times log 3, so I'm just going to divide by 2. You could do this a different way. You have a log. You want to get rid of the log, you use an exponent. Gosh, how many times is 3 to the 4th going to show up? Goodness gracious. This goes away. X equals 3 to the 4th. Add 1. Understand that this is 2 times. Divide by 2. Get rid of the log base 10 with an exponent 10 to the. Exponents get rid of logs. Logs get rid of exponents. 10 cubed is 1,000. Don't be afraid. Add 5, divide by 3. $335, look at that. Sometimes you have to use log properties to solve a log equation. You see logs separated by addition. You should be thinking multiplication. I'm going to take x and multiply x into x minus 4, giving me log base 2 of x squared minus 4x. I see a log base 2. I need to get rid of it. 2 to the power will get rid of a log base 2. Exponents get rid of logs, giving me x squared minus 4x equals 2 to the 5th. 2 exponent 5th, 32. This is x squareds and x's. The only way to solve this equation is to bring everything onto one side by subtracting 32. Factoring. 2 numbers that multiply to get 32 and add to get negative 4. That's negative 8 and positive 4. X minus 8, x plus 4. Giving me solutions, x equals 8 and x equals negative 4. 8 works. You're allowed to take the log of 8. Negative 4 does not work. You're not allowed to take a log of a negative number. Okay, so this is what we call one of those fake solutions. It's a fake out solution. We think it's a solution, but turns out it doesn't work. Okay, last 5 questions. 4 questions is when we solve real world situations. Remember last unit, real world exponential situations? Now we're going to find the same answers just without using Desmos. We have to understand that this is like our normal situation and this was our continuously compounding situation. Okay? Initial rate as a decimal. Time. Final. Car is bought worth $27,000. Depreciates by 12% a year. How long until the car is worth $12,000? Okay, set everything up. $12,000 is my final number. My car started at $27,000. 12% per year. Change that 12% into a decimal by dividing by 100. 0.12. Since it's depreciating, it's getting lesser in value, it's decaying, I can say that's negative 0.12. And I'm going to go ahead and add the r into 1. I have this equation 1 plus r. And I get this value less than 1. It's important when I'm multiplying by a value less than 1, this initial value is going to decrease every year by 12%. Okay? Probably should have shown you this where it's y equals a times 1 plus r to the x, or 1 minus r is negative. This needs to be less than 1 to depreciate your initial amount, or you're going to get an answer that's negative. Every single time we have to understand we're multiplying these things together. You can't multiply the numbers, so we just get rid of it. Divide. 12,000 divided by 27,000 is going to be the same as 12 divided by 27. It's 0.444. I need to get rid of the 0.88. I will do a log base 0.88. A log base 0.88. Six point 422 years. This goes away, X stays away, boom. $12,000 invested in a savings account grows per year. We're going to use the y equals a times 1 plus r to the x. How long until the savings account is worth $18,000? Okay, so I start with $12,000, growing at 3%. That's 0.03. I'm going to take 1 plus that positive 0.03 to get 1.03 to the x, which I'm trying to find. How long until it's $18,000? Okay, divide by 12,000. 18,000 divided by 12,000. 1.5. Get rid of the 1.03 as the base of an exponent by log 1.03 to both sides. $13.717 years. The last two deal with continuously compounding, which means we're using the equation y equals a times e to the rx. It's just a different equation because we're talking about splitting our rate infinitely many times, given to us infinitely many times per year. You will always be given r as a decimal. You don't have to convert it. You start with 10 cockroaches, compounding continuously at a rate of 0.6 per month. We're going to not worry about changing any formulas. How long until the cockroach population is 5,000? This answer might scare us. Make sure you understand it's 10 times. So I'm going to get rid of the 10 by dividing. I get 500. I'm going to get rid of the e by log base e. Log base e is the same as the natural log. The natural log of e to the power is just the power. The natural log of 500, 6.214, ... But the last step is to get rid of this 0.6. So there's one extra step, which sometimes happens. Divide this entire number by 0.6. And we get 10.357. Months. Zombie apocalypse struck the state of Texas. The healthy population at the start of the apocalypse is 29.53 million. The amount of healthy people can be modeled by a continuously compounding equation. Oh, they're even giving me the equation. That's great. How long until there's 1 million healthy people left? So 29.53 million. How long until there's 1 million? This works. You don't have to put extra numbers. Divide by 29.53. You get this decimal. Let's not worry about this decimal and the next decimal we're going to see. I got to get rid of the e. I'm going to use a natural log or a log base e. You can do log base. You can do log log of that number divided by log e, if this is how you've been doing it the entire time. Okay, we get this negative 3.385 ... equals negative 0.7x. Divide by negative 0.7, divide by negative 0.7. 4.836 years. Okay, we got time. Though we went from 29 million to 1 million. It's a lot of people, a lot of zombies. Okay, guys, this is like real world stuff here. So I hope we understand this and not be intimidated by logs. It's just what we're going to do to get rid of an exponent. We've been studying exponential equations. Now we can solve them. I'm out. Thanks for watching, Haley Mitchell.